So we were discussing Green's theorems. Green's theorem last week. There are two versions of Green's theorem. One is if you want to measure the circulation or work done of a vector field on object when you move along a simple closed path. Yeah. So and if your this domain is simply connected, yeah, you can use, yeah, so you can use Green's theorem, and let's assume the vector field is, yeah, so continuous, very smooth, and yes, and this is simply connected domain. Then you can apply Green's theorem instead of computing that line integral. Without computing that line integral, so this line integral, so why do you compute line integral if you want to so here you have your vector field, two-dimensional vector field, right? Not three-dimensional. So here we just focus only the two-dimensional vector field. So if you want to measure the tendency for vector field to be aligned the circulation, to be aligned the tangential vector to the curve, so you compute the line integral. So this is the line integral f dot dr, right? Or ds, we can rearrange this. So we can rearrange this ds dr, yeah, dr. So this is a line integral, right? So without computing this, if your domain is simply connected, and then you can apply Green's theorem. So which is same with this double integral. So without computing this line integral, I think you can compute this double integral. Sometimes it is easier to compute double integral than this line integral. That's why. So just check the region is simply connected, yeah, and C is piecewise smooth, and vector field is smooth. Yeah, vector field is smooth over this domain, and C, and then you can compute the line integral. That means circulation of the vector field along the curve C. Right. So this is the one of forms of Green's theorem. And yeah, so for that we split. So how do you prove this? Yeah, you can chop off this region into small, very tiny rectangles, right? So then you can compute the circulation along this geometry, along this path, piece by piece, because it is piecewise continuous, right? Piecewise continuous. Yeah, so finally, when you compute this, you get, so what is this? This is the, yeah, circulation density. That means, so this is same with the curl, kth component of curl of F. This is same with, yeah, so kth component of dotted with k unit vector. So d, yeah. So kth other two components, I think become zero, right? So because this F, the field F is a two-dimensional one. So P, the first function, this is a function of x and y. Another function is Q, x, y, and there is no z component. Yeah, so when you take the curve, you get only eighth component, right? You get only, which is this one, yeah, circulation. Yeah. So locally, so you get a local property. So this is a, yeah, curl of, yeah, so circulation of the vector field at a certain point. If you sum up, yeah, that local property throughout the entire domain, what do you get? So you don't get any effect in inside the boundary because it is canceling these, yeah, these things. And finally, what you get at the boundary, so finally you get the circulation, or the circulation of the field along this boundary. Yeah. So that is the, yeah, first version of Green's theorem. Yeah. So you can take different geometry. This is it is better to use rectangular coordinates because this is rectangular type, and if you have circular geometry like this, yeah, circular geometry, better use polar coordinates, right? Yeah. And this is the next version. So here we measure the tendency for the vector field to be aligned to the normal vector to the curve, normal vector, or you compute the flux across the boundary. Yeah, flux across the boundary. So always spreading out from the so we want to count, we want to compute how much your vector field force, it could be force field, gravitational field, spreading out across the boundary. So then this so this is perpendicular to the boundary, right? So we want to measure that. So to measure that, so how do you measure the flux at a certain point? Or so so this is the flux into the point, right? So you could yeah, you can find the divergence of the field, which is the flux at a certain point. Sometimes you get positive, that means that point acts as a source. If you get negative, flowing into the field is flowing in, then flowing out. If it is positive, flowing out, then flowing in. Yeah, so basically we compute the flux, measure the flux of the vector field to the point. So if you sum up throughout this domain, what you get? Yeah, this time, yeah. So this is this is the flux density, flux across this boundary here. The tendency for the vector field to be aligned with normal vector to the boundary, to the curve. Yeah, so this is the curve, see? So that, so we sum up, yeah, we measure the tendency for the vector field to be aligned with the normal vector. This is the normal, this should be, yeah, normal vector, yeah. So the normal vector, unit normal, outer normal, out. So this is outside, yeah, flowing out, yeah. So this is no unit normal, yeah. Better take unit normal, yeah. Yeah, so this is the flux form. Now, yeah. So this is the summary. Yeah. So today we are going to discuss surface integrals and the divergence theorem, right? First, let's talk about surface integrals. So earlier we knew how to integrate along along this path. So this is one dimension, right? So this is not a surface. This is a line, arc, right? This is an arc. So we computed arc length, right? Arc length. Well, yeah. So we computed arc length, and today we are going to compute the surface area of any shape. So this is a three-dimensional surface. So how do you compute the area of this three-dimensional surface? So we are going to do that. So remember, so we all the time so write this curve in terms of a parameter t, right? So when you using one parameter t, so we parameterize this curve, this space curve. So this line in three-dimensional space. So for that you need only one parameter. To parameterize this kind of surface, how many parameters do you have to consider? How many? So to parameterize this line, this is something like very simple. This is a line. So it is enough to have one parameter. So if you want to parameterize this surface, so how many parameters do you want? So if you slice off the surface, you get these lines. How many parameters? You need two parameters. Good. Two parameters. So earlier, so how did we? So this is a space curve. This is surface. Space surface. Surface. This is a space curve. So to parameterize this curve, you need only one parameter. To parameterize this surface, so here we go. To parameterize this curve, space curve, you need only one parameter, which is t. Right? To parameterize this kind of surface, you need two variables. One is u, parameter u, and the other one is v. Then you can parameterize this surface very easily. So so earlier we wrote x, y, z in terms of t, right? This time we write x, y, and z in terms of these two parameters, right? So let's see how do we parameterize these kind of surfaces. First surface, it is a plane, infinite plane. It is a plane. So how do you parameterize this? So let's parameterize this. So using two parameters, we can parameterize this surface. So let's do that. I will pick so x is equal to u, very easy, y is v, and uv written in terms of x and y written in terms of u and v, and z also the coordinate using this equation. So you can solve this for z can be written in terms of u and v. So 6, I put this term to other side, then negative 2 x equals this. So therefore 6 minus 2v and other one plus 3 times v. So you parameterize the surface. So this is R. Remember earlier we used R of t. So this time you have two variables. You can parameterize this. Yep. So R has u and v. So what is my vector equation? Yep. Yeah. So u comma x component. So a function of x that depends on x. That depends on u and v. So here we don't have v here. And this is y component, and z is this guy. Yeah. 6 minus 2u plus 3v, like that. You can parameterize. Let's parameterize this surface. So this is the equation of cylinder and centered at 0, 2, right? And the radius with the radius 2. Yeah, so let's parameterize this. So how do you do that? Yeah, x. So I will how to do that? I need space here. Yep. Yep. So x squared squared x squared plus y minus 2. 2 squared. So centered at what is the x, y, and z. So the axis of the cylinder going through 0, 0, 2. Yeah. So this is the axis of the cylinder, and the radius is 2. Yeah. So this is infinite. Yeah. So this is the cylinder. So yeah, we can use the trigonometric identity. Square 2 square. We know cosine theta plus sine theta is equal to 1. This is equal to, yeah, x is equal to 2 cos theta, right? And y is y minus 2. Oh, yeah, y minus 2 is equal to 2 sine theta, right? Or y is equal to, yeah, I take this term to other side. So everything written in terms of 2, what happened to z there? Z can be, look at that. So we have that z, okay. So can be, yeah, so so let's see, R can be written in, yeah, Z is, yeah, so R is a function of theta and the other variable is Z, right? So, or you can use, yeah, U and V if you like, yeah. So Z equal Z, yeah. Okay, X coordinate 2 cos U, Y 2 plus 2 sine U, and other variable. Yeah. So like that, you can parameterize. Yeah. So can you parameterize this one also? Yeah, you can do that. Yeah, let's do it. Let's see. X squared. So this is a surface of the ball. Yeah, x squared. Y squared. Z squared. This is 3 squared. Yeah, the origin is the center, and this is a sphere with the center at the origin with the radius 3. Can you put Z? Yeah, you can put any letters if you like to use X, Y. Yeah, so this should be, so this is U and V. So if you use different letters, yeah, you can use theta and Z. Yeah, right. Put theta there and this is Z, right? So anyway, so you can write any surface using two parameters. That's the main thing, right? Could be any letter. You can use this is X or Y, anything, right? Any letter, any two letters, right? So yeah, this is a sphere. So you had to use, or you better use spherical coordinates. I think I didn't have time to explain. Yeah, I will briefly discuss that. Um, the sphere radius is 3, centered at the origin radius is 3. Yeah, take a point on the sphere. This is on the sphere. So this is on the this point. So what is the rectangular X, Y, and Z? I think I better draw a good picture there because we haven't done rectangular coordinate, no, spherical coordinates. X. So my drawing is terrible. Try to make this clear. Oh my God. So this is a sphere centered at the origin and the radius is 3. I take a general point on the sphere. The coordinates are x, y, z, right? Z. I write these x, y, z in terms of spherical. Yeah, spherical. Yeah. So so you write x, y, z in. So if your geometry is spherical, so you better better use spherical coordinates, right? So because here we are talking about three-dimensional surfaces, right? That's why this is called cylindrical coordinates, right? So x, y, polar coordinates, three-dimensional version of polar is cylindrical, right? So this is x, y, z. Project drop the perpendicular. So drop another perpendicular to x-axis. So this is x, this is y, and so this is z, right? So you can write this x and y in terms of theta and r, right? X is r cosine theta, y is r sine theta, right? Because it is 90 degrees. And the other one is z. We keep as it is. So this is the cylindrical coordinates. Spherical. So let me go to this picture. Spherical. Let's write. So drop a projection. Yeah, I drop a perpendicular to OXY plane. Okay, I remove that sphere. Otherwise, this drawing becomes a mess, right? So I remove that. Okay, so this is a perpendicular. This is a perpendicular to XY plane. Okay, I drop another perpendicular to x-axis and y-axis to these perpendiculars from this point. And consider, so this is this one. And yeah, wait a second. Yeah, so I'm still trying this. Yep. So let's pick a variable rho. Rho is this radius of the sphere, right? Rho. Okay, I will put another angle theta. No, I will choose a different letter. So this is theta, and this is phi. Oh, what happened to this shape? Don't know. Yep. So here we can write x, y, z in terms of rho, phi, and theta. And this is also x is this one, and y is this one, and z is this one. And range of rho and these three parameters are given here, right? Rho can be varied between yes 0 and within these two limits. These two within these two numbers could be 0. Yeah, so theta between 0 and 2 pi, and phi between 0 and pi, right? So this is called cylindrical coordinate. So you can convert this rectangular coordinate or Cartesian coordinate to cylindrical. So you can write x, y, and z in terms of rho, phi, and theta. Right? So like that, you can convert any surface. You can rewrite. So you can parameterize your surface. Yeah, in terms of two variables. Let's say u and v. So you know how to do that. All right. So now we are going to find the area of this surface. How do we find? So very easy. We use this map to compute the area of this deformed surface, right? So this is a surface, general surface, and the corresponding. So if you consider the parameter value u comma v, and the corresponding point is this. This is the corresponding point. So this maps this point on this plane, right? Now we are going to we are going to calculate the surface area of this one, right? So here, so look at this. I label these two planes. This is my plane R, right? This is I label these two planes. So this is my plane R, and this is I label this one as uppercase sigma, right? Uppercase sigma. So this is plane R, right? And this is upper sigma plane, right? Okay, now I split this one into tiny rectangles, very small, small infinitesimal rectangles. So this is then this length is, so this is the variation u. This length is delta u. So this variation is small delta u. We can use d also, delta u, and this is delta v, and you consider this the rectangle. Yeah? So area of that rectangle is dA, right? Delta v times delta, that area of that one, and you find the corresponding points on this plane. Yeah, right. So this is the so this point maps to this one, right? And so here we go. So So then if you have this vector here, this you can, so this is the vector, and if you consider this a length, delta u length, and then here you have, and you will get, and for this point, you, so what is the corresponding vector? R u plus delta u. Yeah, so I think this makes sense. Delta u comma b, and similarly here, so r u comma v plus delta v, right? So if you have this point and that point, let me zoom this in. Yeah, yeah. If you have these 2 points, you are, because these are very tiny rectangles. This is a yeah. So you can consider this is a, yeah, line segment. Yep, very tiny. Yep, very small. Right. So you can find this vector. So which is same with the tangent to the to this curve. If this one, yeah, if you take the limit, delta goes to 0, then you get the tangent to this curve here. So this curve, I will draw a different color. Yeah, this curve. Yeah, this curve. Yeah, yeah. So that vector would be the tangent. Yep, here this one. Similarly, you can get the tangent vector to this curve here by taking the difference. Yep, this one minus this. Right. So you have these two tangent vectors, right? If you take the cross product, so so you have that, and so this one and this. Let me. So I hope this makes sense, right? Then this makes sense. Yep. So let me draw. So this is so this one del this length is very tiny. So you have this vector and that vector. If you take the cross product, you get the normal vector at this point. As well, if you take the magnitude of that, you get the area of this parallelogram, right? So this surface is yeah, this one is a little bit deformed. That's why so you don't get this rectangular. You get, yeah, something, yeah, parallelogram, something like that. If you take the cross product of those two vectors, you get the area. So yeah, let's yeah. So let me scroll down a bit. Yeah, so yeah, you get that. Yeah, just, which is as a adjacent side. Yeah, so this is the other side, and then, yeah, then you can take the, yeah, then you can take the cross product. Yeah, this is, and the magnitude of that cross product is given by the area of this parallelogram. Yeah, area of this parallelogram, right? So what is that? Yeah. So cross product. So that the what is the direction of that cross product? Yeah. So you get this unique vector, right? Unique vector. And if you get the magnitude of this cross product, yeah, you get the area of that parallelogram, right? So, right. So you have this area, right? Yeah, which is same with, so what is this? Which is same with delta sigma. Let's say d sigma. Yep. So here you get infinitesimal, uh, yeah, area bit on this plane. So this is your d sigma, right? So this one is dA, and this is your d sigma. Yeah, so and this is the normal vector. That means the cross product of these two vectors. You can rearrange these two vectors by dividing delta u and delta v, right? Delta v, and you can take the limit. Take limit to the zero. What is this? What is the definition of this? This is partial sum, partial derivative of r with respect to u. So I will write this notation, partial of r with respect to u. This is partial of taking limit delta v very infinitesimal. That's why I said before, very tiny lengths. These are very tiny. This length goes to zero, then this becomes the tangent. Yep. So partial derivative, partial with respect to v. So here, so when you take the cross product of these two, this is the the area of the parallelogram, right? Let's denote it is let's take it is delta sigma. Yeah, we know that when you take the limit as delta u and delta v go to zero. Yeah, so you can write this term to partial with respect to partial of u with respect to u, partial of r with respect to v. Yeah. So just take this term to other side. So this is approximately equal to partial of u. Yep, so take this term to other side. Then you can, so this area of that parallelogram, which is d sigma, this one is equal to cross product of these two times these are scalars. So this is, what is this? Delta u times delta v. Delta u times delta v is denoted by dA. This is dA. This is equal to, what is this? I will write magnitude of partial derivative with respect to u cross partial derivative with respect to v, and this is dA, which is equal to, so what is this area? This area is the area of this parallelogram. So this is infinitesimal area. So let's denote d sigma. So d sigma. Finally, d sigma is equal to, so this is the, so what is this? This is the normal vector. This is normal vector to the surface. So cross product of these two is the normal vector to the surface. This one. And if you take the magnitude, that means the area of this infinitesimal parallelogram, which is denoted by d sigma. D sigma is equal to magnitude of that cross product of these two partial derivatives times the area of this side, the infinitesimal area of this. So this is the relation. So if you integrate, if you add up these infinitesimal area parts throughout the entire sigma, you get the surface area. So sigma throughout the entire sigma d sigma is equal to, so you add up this thing times dA throughout this region R, throughout this region R. So let's denote the surface area of this geometry. This surface is uppercase S. So let's denote uppercase is the area of this sigma plane surface, right? So therefore S, this is S. Yeah, S is equal to double integral, yeah, magnitude of this cross product. This is the normal vector, and we consider the magnitude of that normal vector, right? Times dA, dA is du times dv. Yeah, so this is the relation. Okay, make sense? Any questions? I think